All right, y'all, we are at the end of Thermochem. Please put away your phones if you still have them out. I want to warn you that this last lecture is your least favorite of the unit usually. I don't think the stuff is so difficult, but some of the stuff's a bit more abstract in regards to getting your brain wrapped around it, especially for an exam. So let's take a look. Those of y'all at home, you should have your slides out for Entropy and Gibbs. So our unit has been focused primarily on enthalpy. So you should be pretty good at delta H, right? You know 5 different ways to calculate it and interact with it. So delta H will still play a role today, but our main focus is 2 new variables, S and G. Whoa. Stupid delay is killing me. So let's start with S. Entropy is a new idea for us. Some of y'all have heard of the word entropy before, though. It's a look at disorder in a system. It turns out that in our system, like our big universe system, that disorder is always increasing. The universe is pushing us towards disorder. It's the reason why if you clean your bedroom and you just live in it for a week, even if you don't try to make it messy, it gets messy, right? Your bedroom automatically becomes more disheveled. It's the reason why if you've ever done laundry for your parents, or maybe your own laundry because you're such good little teens, that after you throw them in the dryer and let it run for 40 minutes or whatever, you've never opened up the door and it's been nicely folded, just sitting there waiting for you, right? Because whenever you leave a system to itself, it always goes towards disorder. Entropy is the measure of that disorder, and it's variable S. What we need to know to apply it to this class is that since the universe is always moving towards disorder, that means that items that increase S are spontaneous. What does it mean if something's spontaneous? It means it just happens, right? It just happens all by itself. And we just discussed that entropy, the disorder of your room, the disorder of the laundry, it happens automatically. Therefore, anytime entropy is increasing, that means it's naturally happening. Anytime we have an S value that is positive, that means it's what we called thermodynamically favored. You wrote down that word on the next slide. This is where we are, people at home. But I want you to underline the word thermodynamically favored there in that second stanza. Yes. Ooh, I didn't check notes. Very good. Oh, y'all are the only class that was still eligible for notes. You want to see if they get their bonus point on their exam? Let's go over to cluster 1, feat 3. Oh, they're gonna do it. Very good, very good. All right. Good job at being my favorite class. What? No, it used to be 4th period. 4th period is my lunch. Okay. Anyway. Thermodynamically favored is our chemistry way of saying spontaneous. So listen again as I connect these ideas together because it's a really good foundation for today. All right. Entropy is disorder. Disorder is what happens automatically. If something happens automatically, we call it spontaneous, but not in here. In here, we're going to use the phrase thermodynamically favored. Since entropy is S, if S is positive, meaning entropy is going up, then all the other stuff is happening. It's spontaneous. It's thermodynamically favored. Zambrano's on her phone. Bunch of cool stuff happening all at the same time. Forever now. She's on her phone. Okay. So let's calculate with it. How do we find this value? Well, the good news is that one of the common ways to find it is Big Mama. So we should be pretty good at sum of products minus sum of reactants. So let's do a quick plug and chug of one of those before we make it a bit tougher. Do current slide for context. All right, taking a look at my data here, you'll see that the table has H, G, and S data. So we're only worried about the S right now. I haven't introduced you to G yet. We'll get there in 20 minutes. But let's prove that Big Mama can get us an entropy value for disorder. So here we go. Start with the products. All right, so in my first bracket, products, there's only one of that first aluminum chloride product with an S value given of 111. So there's all the products. Minus, because it's products minus reactants. Now, notice that both of the reactants here are free elements. Prior to learning S, we knew that H, enthalpy, free elements didn't have a heat of formation, so it was always zeroed out. Notice that everything has an entropy value, all right? So the S's for free elements do have values. So the first one for the aluminum in my reactants is 1 aluminum at an S value of 28 plus sum of 3 halves chlorine at an S value of 223. Correct. Yeah, because the STP is 273. Yeah, I'm about to talk about that, but only gas laws has the standard conditions of 0 Celsius. Everywhere else has standard conditions of 25 degrees Celsius. All the other units of the class. Hopefully you're plugging and chugging. By the way, I forgot to mention, this slide says find delta H, and we're finding delta S. That's my bad. You could find delta H with Big Mama, but we're doing entropy, so you can change that if it's bothering you. But I'm finding delta S of the reaction, which is the system. And I get an answer. Anybody want to shout? Yeah, I'm just going to put negative 250. These are all constant values, so the sig figs are not really held accountable, but there's a 2 sig fig, so I'm going to do a 2 sig fig, whatever. It's probably best practice. And you'll notice, though, that it's joules. I want to really point out the joules there. If you look at the columns of H to G to S from the slide, you'll see that the standard units for enthalpy and Gibbs is kilojoules, while entropy is joules. Please make a mental note of that, because whenever S and H have to slam into each other in an equation, they have to be in the same units, and they naturally aren't. So you're going to see us fix it a couple times today, but it's a big deal. We all right? Big Mama should not be throwing us for loops at this point. Now, I do want to point out something. In the table, it's got the NOx symbols. Those little O's up there, all right, they look like degree signs. That means standard conditions, all right? We've talked about that before. But standard conditions is 298 Kelvin. That's automatically the temperature that this data is true at, which is an important number to know, all right? That's the 25 degrees Celsius that was standard prior to gas laws. All right, well, let's get into the slightly more fun stuff. just like enthalpy, your delta H, there are multiple perspectives of entropy. Delta S, the system, the surroundings, the situations, you can look at it from two different sides. All of that stays true. But here's a more important idea. The delta S, this sounds silly, but the entropy of the universe is what we really care about in regards to drawing conclusions. You know how a moment ago, I shouldn't have erased it. You know how a moment ago we got negative 250? All right, this was our S value. This value was of the system. You can't draw a thermodynamically favorable conclusion based off of delta S of the system because there's other variables at play. The way that we know whether something is truly spontaneous is how it affects the universe, how the numbers talk to the entire universe. And this number was not that. Here's my point. If you're being asked to say if something happens automatically, is it spontaneous, thermodynamically favored? If you're doing it based off delta S, you need delta S of the universe, which is found by combining the system and the surroundings. So that leads us to these other equations, which, as I said, makes this lecture a bit more annoying. In order to find the entropy of the surroundings, we've got this other equation that brings enthalpy into the mix. So with that said, and these equations available, let's look at an FRQ. This is an FRQ from about a decade ago. You can see the beautiful lettered parts. Let's see if we can get all the points. Part A says, calculate the entropy of the system. Now, make sure the vocab doesn't start throwing you for loops, all right? Entropy is S, enthalpy is H. Get it all straight in your head before next Friday so that you don't get drowned. Calculate the change of entropy, for the system. All right, well, look, they give us a reaction, they give us a data table, y'all, it's Big Mama again. So let's do it real quick. All right, the one product that we have is made up of two ammonias. So it says two NH3s. The NH3S value is 193. There's all the product information minus the sum of the reactants. It looks like there's one nitrogen in the reaction with an S value of 192 plus some 3 hydrogens with an S value of 131. If you run it, I've been running out of time today, so I'm just kind of clicking ahead, but I believe in your ability to push those buttons. I get an entropy of negative 199 joules. And we have found the answer to part A. We have earned a point on our FRQ. Yep. Yeah, you do. I'm just out of board space here. But yeah, so it would be Kelvin per slash mole Kelvin. All right, but those joules units are really going to be important here in a second. Let's move on to part B, which will be the super annoying part. Bear with me here. Calculate the change of entropy of the surroundings. We have not yet used this new equation. But look what we need to know. First off, look here. You see that negative symbol? There is an inherent negative symbol in your new equation. That's an important thing to notice. But we need the enthalpy. All right, well, you know 5 ways to find enthalpy, but based on a given table like this, Big Mama's the best way to go. So let's big mama delta H right up front so we have a value to put into that location. In order to find delta H of the system, we are going to big mama. Again, starting on the product side, the two ammonias have an H value of negative 46.1. And what's true about the reactants? They're all free elements, and we know that for delta H, free elements are zeroed out. So yeah, it just basically looks like this, which is wonderful. So we can get that delta H value right away of negative 92.2 kilojoules. Here's where there's some fixing to do. The most obvious fix is the unit issue. We are ultimately trying to end with S information, right? This question wants us to find a delta S. As I said earlier, entropy is measured in joules. So what we're going to do is I'm going to try to get everything pushed towards joules when I can, since they need to talk to each other in those units. So let's not keep this number like this. Let's immediately turn it into joules, which should be easy. If kilojoules is going to joules, the unit's getting smaller. So the number gets larger, and kilo is 3 slides. This should become negative 92200 joules. And there's a usable version of the number. Yes? You don't. Well, they're both dealing with Kelvin. It's actually good that they're not in both mathematically at the end because it's there because we're going to get rid of it. Yeah, when we divide by it, it'll go away. So the easy answer is no. You don't need to even think about that. Now, here's the other thing, and I don't know the best way to teach this. This is how I do it. Look here, look here. We are about to just plug in these numbers, right? You have the temperature, I promise. You might not realize you do, but you have the temperature. But you see that negative symbol? What's going to happen when we throw that negative symbol in front of that number right there? It's going to become positive. What I like to do is preemptively fix it. I'm like, okay, basically this negative symbol always, it just switches the sign of whatever you got at this point. So I'm just going to do that. There's the number that needs to go right there. So I've already taken care of that. So in order to find the delta H of the surroundings, which is what this wants us to find. Woo, S. Cummings is messing this up. It is the negative delta H. I've already fixed that. So there's the number. It's going to be this delta H divided by, what's the temperature? 298. Because you see the knock symbols in the table? It's that standard 298, which means, boom, we now know that our answer is 309. Yeah. Part C. Calculate the entropy of the universe. There's the other equation, but he's a really easy one to use, yeah? It's the sum of the system and the surroundings, and we've got all those numbers here. Here, I'm going to box this dude. All right, there's the two answers that got us the points on our FRQ so far. But yeah, the delta S of the universe is going to be the sum of the system and the surroundings, which will give you a grand total of 110 joules. Samantha, you're leaving. Hey, is the reaction, part D, question D, thermodynamically favored? Yes, but make sure you look at the correct number. Look, one of your delta S's, one of your entropies was negative. Remember, for it to be thermodynamically favored, you need a positive S. But this one doesn't matter, right? Because the one that truly determines it is the universe. So the answer to that question then is yes, because entropy of the universe is positive. For part D, I'm not going to write it. Yes, because delta S of the universe is positive. Bye-bye. Do you want to come say bye? No? Nobody wants to be famous. Yeah. There you go. What you think? It'll take practice. Like, there's lots of little things in there, but let's take a math break. We'll get conceptual for a little bit. If it wants you to identify entropy using no numbers, there's a list to go by to know whether or not situations generally increase or decrease disorder. So here they are. This is pretty easy, I think. Gases have more disorder than solids. So if you're going that direction towards the gaseous phase, it makes sense that everything's in a less predictable pattern. We know that our solids have that structure, right? A lot more structure if you think about your particulate drawings. Well, that's less disorder, whereas the gases, they get to move around wildly, all right? Like the definition of entropy. Another way to know that entropy is increasing is forming a solution. If you drop a solute into a solvent and it dissociates, those particles, ions, have the ability to move around more freely. More disorder, right? When they're bonded in that compound, well, I mean, they're more stationary, if you want to look at it like that. But the dissociation allows them the ability to live their best free life. Number 3, volume increased in a gaseous system, which rhymes nicely with our last unit. If you have X amount of gas moles floating around in a balloon, and you take that exact same amount but put them in a larger balloon, well, guess what? They have more room to roam, and they'll bounce around a bit more wilder when they're allowed more space, more disorder. Finally, the gray area one, focus, because this one can trick you. The rule is that increasing temperature increases entropy. That's only true, though, for sure, in a singular sample of something, like in a physical change. Like, for example, if I take this metal can, this empty metal can, and I just put it on a hot plate, well, the metal can just gets hot, all right? Just a temperature change. There's no reaction there. And this is true then. The particles in the metal's case, the sea of electrons, will move faster, all right? And that's more entropy. Rule number 4, though, cannot automatically be applied to a reaction. Sometimes it can, but here's the deal. If you have a reaction where you are forming a solid, the end product is a solid, well, what happens if you heat up that reaction theoretically? You would make more solid faster, which would contradict rule number 1. So you've got to be real careful. Increasing the temperature of just a sample of something physically, that will increase the entropy. But if you're doing a chemical change, there's a chance that heating it up would be producing something that naturally has less entropy, depending on its state of matter. So be sparing when you're doing reactions with rule number 4. Then it would apply, right? And I'm going to show you reaction examples in a moment, as you know. But let's do this bottom part real quick. There's 3 examples to practice. I'm going to give you 20 seconds. I want you to decide before I draw cards if each of those will increase or decrease entropy. Bernal, you're wanted in counseling when I'm done teaching. So it'll be the very end of class. Let's see how you did. Remember, does it increase or decrease the disorder? Ice melts. Let's go over to cluster 3, seat 6. Hey, 3-6, what do you think? Increase is correct. If it's melting, it's becoming more towards the gaseous-ish phase, solid to liquid, more entropy. A precipitate forms. Let's go to cluster 6, seat 1, Aspen. A precipitate forms. Say again. Decrease. A precipitate is a solid. All right, here, toss them to me. A solid forming definitely goes against disorder. He's supposed to be over there, except for you have a bunch of empty desks that aren't supposed to be empty, so hopefully this next one doesn't draw Aspen. A solid dissolves in water. Let's go to cluster 3. Yay. Seat 4. Hey, 3-4, what do you think? The third one. A solid dissolve. Say again? Increase is correct because of rule number 2, a solution forming. Yeah? Yeah. I'm just going to answer these ones for you, so I would have a writing utensil up. But you'll notice we've got these reactions here. So if you look at, for example, the first reaction, do you see how you end with a solid? All right, so right away, the reaction itself is producing a solid, therefore, entropy decreases. Less disorder. On the second one, do you see how there's more moles of gas when it's done? There's only 1 mole of gas at the beginning, but 2 moles of gas at the end. That's an increase in entropy. You could even apply bond theory there because the reactants are more bonded together, whereas bonds have been broken to create those products. And again, that would give them more freedom to roam, more disorder. And then that last one, there's 7 moles of gas on the reactant side. I'm sorry, I can count. There's 9 moles of gas on the reactant side, only 4 moles on the product side, so less gas when it's all done means a decrease in entropy. Y'all are very quiet. Are we enjoying this? I'm missing 10 students. So. All right. Let's move to the end of the unit then. The final variable to introduce to you is G, which is Gibbs free energy. While enthalpy, H, tracks energy movement in a specific system, in a specific reaction, Gibbs takes a step back from that and just looks at all of the energy present, whether being used or unused. The reason that Gibbs is really helpful to add in at the end is because the sign of G automatically can tell you whether you are spontaneous or non-spontaneous, thermodynamically favored or not. Whereas delta S has all this extra stuff, like it gives you an S value, but is that the universe? You got to do all this extra stuff. G is more concrete. If you have a negative Gibbs, you are thermodynamically favored. So it's supposed to be more straightforward. It comes with an evil little table that I feel like defeats the whole point, but it's supposed to be helpful. Now, I want to point out a couple things. First off, Big Mama works for G. If you're asked to find delta G and the temperature is 298, the standard temperature, then you can Big Mama the data. Products minus reactants, sum thereof. If the temperature is not 298, which on the AP exam, a lot for delta G, it's not, you have to go ghetto homies. I'm sorry that I call it ghetto homies. I had to memorize a bunch of equations to get my composite certification to teach any science in the state, and they don't give you a formula chart on that exam. So I had to memorize hundreds of equations. Ghetto homies. Anyway, if you're finding Gibbs at a temperature other than 298, then you are going to let H and S talk to each other mathematically to figure out a value for G, which again, if it's negative, it is thermodynamically favored. Before we do a ghetto homie problem, I want to introduce you to the terrible table. If you look at the way the table's written from the slides that you copied or paused, I want you to notice that the last column has G being negative. You see how the last column refers to a delta G less than 0? So they're all assuming that G says we are thermodynamically favored. What the table does is it splashes the different temperatures into the mix because T is a part of ghetto homies. Now, y'all need to know this table. It's a bummer of a thing to get good at interacting with, but there's always an MCQ question over this. If you walk into the AP exam not knowing the different, if H is high and S is low, or they're both high or whatever, compared to different temperatures of delta G, you're going to miss that question. I mean, you're just going to be, you'll have a 25% chance of guessing it. So know this table. Of the different entries, the one that I think is most interesting to really have on your brain is that second row, where it says if enthalpy is above 0, entropy is below 0, and delta G is below 0, meaning we know that that S is low and not high, that there is no temperature by which you can make the reaction spontaneous. It means that if you plug numbers in, matching those higher and lower, you can never find a temperature that will make it thermodynamically favored. Anyhow, as you interact with that table and apply it to some of my questions, you'll see how you're supposed to get your head wrapped around it. But it's a more direct route to figuring out thermodynamically favored or not than having to use these extra equations like we did on our FRQ. Let's get a homie ones. This problem asks us to find delta G. All right, so we're going to Gibbs. Remember, if everything is standard, you can use Big Mama, and actually all this data is standard. We could use Big Mama here, but we want to practice ghetto homies, but you'd get the exact same answer. Anyway, let's look at our variables of ghetto homie and get them all plugged in. I want to point out first that in order to do it, you need an enthalpy and an entropy. And with a table given like this one, we can Big Mama both of those. So let's start by finding H. All right. Using the table, starting with the products, it looks like there's one aluminum chloride. The H value of him is negative 704. Just like in an earlier reaction, the reactants are all 3 elements. So hooray, the delta H being negative 704 was very easy to find. All right, so here's one of our happy little variables that we're going to need. Ghetto homies also requires an entropy of the reaction, which we know we can use Big Mama for that as well. But here's where I made our life easier because we all know we're running out of time right this moment. We've already found delta S for this reaction. If you go back to the very first calculation we did today, it was same table, it was same reaction, and the answer you got was negative 250. You got negative 250 joules in an earlier slide today for this problem. But I'm not going to put a little squiggle line around him because ghetto homies puts S and H together. They can't be in different units. Now this time though, I'm actually going to push towards kilojoules. The reason is that my end game is delta G, and delta G lives in kilojoules. So let's push this number towards him to make it more user-friendly. If you're going from joules to kilojoules, the unit's getting bigger, so the number gets smaller. Kilo, 3 slides. Slide it 3 times smaller, and you'll get 0.25. Now I've got another fun variable for my plug. Now we can find the Gibbs. Plug and chug ghetto homies. The delta H value is negative 704 minus the temperature times delta S. So I'm going to put them in parentheses for math reasons. Now here's where ghetto homies is useful because you can put any temperature in here. If the temperature is standard 298, then you could have just used Big Mama. And this one is standard because of the knock symbols in that table. But anyway, we forced ghetto homie. So the temperature is 298 Kelvin times the entropy of negative 0.25. And voila, you get a Gibbs value of sig figgy, approximately negative 630. Those of you at home, there's one more problem in the presentation. It's really important to watch, but the bell's about to ring. So in my other video, I'm going to find a way to splice this better. But in the original video from 6 years ago or whatever, the very end of it, there's 5 minutes worth watching of that final Gibbs problem. Hey, spontaneous or non-spontaneous? What? Spontaneous, negative Gibbs is thermodynamically favored.